Okay, so last time we learned about how to train this LUNET architecture, and the LUNET is defined like this. Okay, and we also learned about the data loader, which is the easy interface to load the data. So I recommend you to use this feature implemented in the PyTorch. So I mean, you have to first define the data class, okay? And then if you make one instance using this dataset class, you have to specify it in the data loader to manage the loading the data from that dataset. So you can specify multiple attribute when loading the data, such as the shuffling or batch size, or whether you will use threading or not, and others. Okay, so this data loader is providing easy interface for loading the data. And one important merit of this data loader is you can just use this data loader in the for loop. Okay, so this train loader is defined here, and if you use this train data loader in the for loop, then your data, their pairs will be loaded. I mean that this follows what you defined here. So this is your data set class defined by you, and I mean the data format you will read in this for loop is defined by this data you defined in get item method of the data set. So if you put your data loader here in the for loop, then it will return the data as you defined in your get item method. So this is actually very important. Are you guys following this? So I mean, we raised the assignment 1, okay, already. And when you implement that, maybe you have to use this kind of data. You have to define by yourself the data set class and the data loader, maybe. So yeah, I wish you understand this, okay? And next, I explained the difference between stochastic gradient descent and also the gradient descent. Gradient descent, it calculates one gradient after seeing all the data once, and then update your data parameter once after seeing all the data. Okay, but stochastic gradient descent, you only see some batch which might be having only 32 images, and then calculate this DL dissector after seeing this partial data and update the parameter using this partially calculated gradient. Okay, so this is also the showing the figure. I mean, this figure is showing the difference between GD and SGD, and this is the full batch, whole training data, and you calculate this after seeing all the data and update this after seeing all the data. But SGD, we have mini batches whose size is small compared to the whole data, and calculate DLD zeta multiple times and update parameters multiple times. So I mean, GD is more optimal in the sense that it sees a lot of data and calculate one best DLD sector. In that sense, it seems like it's more optimal. But the thing is, the data used for calculating this DLD sector is the training data, actually. And I mean, we are wanting to make some model, model and its parameter sector. We are wishing that it generalized to the unseen testing data, and that testing data is different from this training data. It's not same. So having optimal parameters for training data does not always coincide to have the parameters which is best for the testing data. So GD could be suboptimal for the testing data. So even though the SGD have some randomness in the middle and it's not that optimal compared to the GD, but in practice, for the unseen testing data, the SGD trained model can perform better than the GD trained models. Okay, so we are actually maybe you will see overfitting phenomenon in the later lectures, and this is meaning the model is overly fit to train data, and it does not perform well, to test data. This is actually the problem, because we always have to consider the test data, because our aim is having good accuracy on the test data, not for the trained data. So, I mean, our model's accuracy will be evaluated by the test data, which is unseen. So this overfitting is actually the problem in deep learning. Okay, so we have to prevent that and have some, I mean, have to train the model which is well generalized to the unseen data. Okay, so that is actually the thing discussed here. So SGD is in practice giving us better performance. And also we saw our actual code for training the LUNET architecture. So this train function and test function, they are training the model using whole data, okay? Using whole data, but they are seeing each mini batch here using this for loop, okay? So you input the train train loader you made, and it if you put that in the for loop, then you will return the data in this X and Y you defined actually in here, okay, get item method of your data set class. And here you can see every partial mini batch, you will calculate the gradient and update the model parameter. So this is actually the implementation of the SGD, okay? And yeah, using SGD, we are implementing the train method and testing method, which is very similar to the train method. But this is first different. We have to set our model in the evaluation model, but in training, we set it in the train mode by doing this. And also in the testing, we don't have any low start backward and optimizer.step comment here, because we are not updating our parameters. So besides that, every line of code are same as the previous train code. Okay. And training loop in here, actually it is train the model for every epoch. So here in this loop, we are looping through the whole epochs. So each epoch means see whole data once. And we will see during the training, we will see if the epoch that number is 100, then it is meaning that we will see the whole data 100 times. Okay, and this loop, inside this loop, we will define how to read one whole data. Okay, and for one whole data here, we train our model once using the train method we defined here. Okay, and also here we have test method for seeing for evaluating the model for whole data once. So here we test the model for one epoch using this test method, and this is visualizing the status during the training for one epoch. Okay, so we will show epoch index and train test loss and train test accuracy here. Okay, for that epoch. And then we will return the model, trained model, after looping through all the epochs. And this is the top code that called this training underbar loop. And we have defined our model, optimizer, and loss functions in the outer of this training underbar loop method. Okay, and this is trained model and trained actually the optimizer. And we have to input some initialized model and loss and optimizer and train and test loader and the hyperparameters for number of epochs. Okay, so this is the implementation of the LUNET training. So doing the assignment 1 because most of things are similar. Okay. And this is the visualized information during the training. So, I mean, here we define some visualization code, okay? And that is actually visualizing these things. So, epoch index, train test loss, and train test accuracies. And as epoch goes, you can see the losses are becoming smaller and accuracies are becoming higher, okay? So most important thing is the testing accuracy. So even though sometimes train accuracy becomes higher, but test accuracy could be not higher. In that case, we will call it as the overfitting. Okay, so we have to prevent it actually. Okay, and now I explain the code for using only the CPU. So using only CPU, the training will take some time. So for 15 epochs, when seeing whole data 15 times, it may take over 15 minutes. It depends on the types of GPUs actually this time. So if you use better GPU, better CPU, it will take faster. But if your CPU is not very good, then it may take more time. Okay. So anyways, it takes time, but there's no easy way to accelerate actually this training time. And we will do that using the GPUs. So the PyTorch is providing you easy interface for using the GPU. So CPU have up to 32 cores. Okay. So now Intel is making some CPUs, but mostly it have up to 32 cores inside. So even though we use some parallelization method, we cannot, dramatically, accelerate the speed. But GPUs, it have many cores, actually more than a few hundred cores. So it depends on the types of GPU. But the NVIDIA GPU, it provides a CUDA library that can parallelly use the GPU cores. And normally GPU have more GPUs than the CPUs. So we actually use this GPU for training the deep networks. Because deep networks, it have a lot of parameters, but individual operations are very simple. So it could be redundantly, parallelized for using the GPUs. So using GPUs will dramatically accelerate the operation time. Okay, so we are now, from now on, we will use GPUs. And this is actually showing you how to use the GPUs in Colab environment. In your PC, you have to properly install the CUDA library, okay, which is the NVIDIA's parallelization library. So you have to install the NVIDIA driver for your own GPU and also have to install the CUDA, okay? So, yeah, but I recommend you to do all the assignment in the Colab. So I will maybe omit this part, but if you want to fulfill your assignment by using your own PC, then you have to do this, referring some web materials maybe. Okay. And in Colab, I mean, the setting the GPU mode is rather simple. So you can see, you can type this to, the first line is importing the PyTorch library, and the second line is for checking whether the GPUs are connected or not. So Torch CUDA is available. CUDA, it is checking the CUDA library is available or not. In your local machine, you also have to check the availability of the CUDA in your Python code using this line of code. And if you do not, by default, the Colab will print out the false for this command, because by default, the Colab is not providing you the GPUs. But in the menu, you have to do these three things. I mean, in the menu of the Colab, go runtime and change the runtime type, then you can see this kind of menu, and you have to select GPU and click the save. And then you can see it may take some time to set GPUs in your Colab environment. And after that, if you do this, then you can see now your CUDA is available. So you have to do this for, setting the environment to use the GPUs in the Colab. And also you have to do same things for your own PC by doing this and checking this becomes true or not. You have to confirm that, okay? And then in the code, you also do something for using the GPUs. And the thing you have to do is actually these things. So you have to copy your data, which is the X and Y, okay? X is input and Y is the ground truth, to GPUs. So you have to copy your data to GPUs. And another thing is you have to copy your model, CNN model, to GPUs. Okay, the thing you have to do is these two things. You have to copy your data and model to the GPUs. So this device is actually defined in the upper method. And this is meaning the GPU. Actually, this variable is having the GPU information. And this X and Y, that's having input data and ground truth data. Okay, so X and Y is loaded from the data loader you defined. And this X, by inputting this .2 device, you can copy your data to the GPUs. So the grammar is very simple, actually. So by doing this, you can copy your data to the GPUs. And also testing code, you also have to do same thing to copy the data to GPUs. I mean, if you miss some of the things, then maybe the error message will outcome saying that your X and Y are not in the same device. So I mean, you have to carefully check your code is properly copying your data, all the data, to the GPUs. And so this is the modified code to get device information from the top code to propagate it to the train method and test method, because we augment the device variable for testing method and train method. We have to also change this part. This is the intermediate method we defined. So we get device information, which is the GPU information from the top code, and propagate it to the train and test method, okay? And in the top, at the top, you also have to augment the method, because we have augmented another parameter for GPU information here, so we have to input it here. And also the thing is, we have to define the GPU information. So This is meaning that if torch, this is saying that if CUDA is available, CUDA library is properly setted, then we will specify the device as the CUDA, else we will specify it as the CPU. So it is saying that if CUDA, that driver is not properly installed, we will use CPU mode. But if it is set properly, then we will use the CUDA, which is specifies we will use the GPU. Okay, so device might be either CUDA or CPU. Okay, depending on your environment. And another thing you have to do is you also have to copy your model defined here, LUNET 5 and classes. This is making instances for LUNET copy that model to GPU mode. So this model will have the LUNET architecture having the random initialized weight, which is saved in the GPU device. Okay, so the model is now also in the GPU, and the data we already copied it. When loaded from the data loader, we copy it to the GPUs. So now the model and data, they are in the GPU. Okay, this is the thing you have to do when wanting to use the GPUs. Then after doing this, and if you run the same code, you can feel that now the time is faster, multiple times faster than previous. The results are almost same as before. The loss and train loss and test accuracy, their tendency is same as before. Because there are some randomness, there could be some variance, but the tendency is same, but the speed, it becomes a lot faster, okay? So this is the merit of GPUs, okay? Any questions till now? No, okay. And from now on, I will explain more advanced CNN architectures. So previously in LUNET, we learned how to implement training that architecture for MNIST dataset, classification dataset. So this was the LUNET architecture we learned. This is very simple CNN architecture. From now on, we will learn the RLXNet, which is the architecture I already mentioned. So, this graph you already seen before at the earlier class, you already seen this. So I mentioned that in the 2012, this is the visualization for accuracy, relative to the years. So this is x-axis, that's year, and this y-axis, that's the accuracy. And this graph is showing the accuracy for best algorithm, the SOTA algorithm in ImageNet challenge, which is the image classification challenge. And so it is showing the best algorithms, not accuracy, actually the error rate of the best algorithm according to the years. So error rates are gradually reduced as the year goes. And important thing is before 2012, that's the shallow learning algorithms, which is the SVM before the deep learning. But in the year of 2012, it shows 10% improvement by the RLXNet architecture, which is famous CNN architecture. And it is having 8 layers, okay? And we will learn about this RLXNet, which is the first successful CNN architecture that records state-of-the-art accuracy in ImageNet challenge, okay? So before 2012, the shallow running algorithm prevails in image classification task. Okay, but after this AlexNet, every research for this image classification or other domains, becoming to change to use the deep architectures. Okay, so this AlexNet is, in that sense, actually very important. And AlexNet, Alex is the name of the person who proposed this architecture, whose last name is Krzyzewski, and his first name is Alex Krzyzewski. He proposed this architecture, so we call it as the AlexNet. And here, the important feature is the ReLU is first used. As you saw in the LUNet architecture, the activation functions are actually the tangent hyperbolic. Tangent hyperbolic is used as the activation function in the middle of the CNN convolutional layers. But actually, this AlexNet pointed out the gradient vanishing phenomenon I already mentioned to you, and they proposed to replace the tangent hyperbolic activation function to ReLU. Okay, and also they use multiple GPUs and can accelerate the training time. Okay, so previous to this the deep architectures have to train by the many data, and also because it has a lot of parameters, their training time is takes a lot of time, but most of persons don't exactly know how to make this training using the multiple GPUs. But this AlexNet is actually the first to train the deep architecture using the multiple GPUs. And also there are some other techniques used, this dropout and data augmentation. This is also very important algorithm to prevent the overfitting I mentioned. Okay. Overfitting I mentioned. So maybe there's no explicit slide for that, but I will explain that in here. So data augmentation, actually, this is very simple. For the data, you have X data, which is the image, and the Y, which is the label, okay? So because this is the image classification task, X is image, and label is some semantic class like the bird, cat, dog, or others. So, but if you flip this X image, if you horizontally flip this same image and make some X prime and make the labels, keep the labels same as before, this is also the correct example. So even though we flip the image in the horizontal way, this image is the same object the X had, okay? Are you agree with that? Okay, so even though you horizontally flip the image, the labels the image had keep same. And you can use this X prime and Y prime as the additional data to train the network. Okay, and also you can do similar things by vertically flipping the image, or if you adjust some color distribution of this same image to make some X2 prime, their labels are also same as before, okay? So even though you adjust the color distribution of the image, the object this image is describing is same as before. So the semantic ground truth, semantic class label doesn't have to be not changed. So you can also use this, image distribution changes samples as the additional data. So this is the data augmentation scheme. Okay. So actually, if you augment the training data, this data augmentation is used to augment the training data. I mean, if you apply 10 times data augmentation for all the samples, then you can augment the training data 10 times, okay? So it is very effective for increasing the size of the training data. And if you augment the increase the number of training data, if you increase the train data, then the overfitting, that possibility becomes less. So, I mean, this is very natural. So, I mean, if you train the model, that overfits to the images that you can hold the images that you can see in the world, then you can see in the world. I mean, if you can take pictures of the images that exist in the world, and then make our trained model overfit to whole data, then this is somehow the ideal situation. So I mean, overfitting is not that bad thing if the trained data is actually same as the data we can see from the world. Okay, I mean, the world, we will call that as the world data. I mean, if we can get the model that overfit to the data that the whole data we can obtain from our world, then it's not that bad thing. Okay, then during the testing, we can, I mean, the testing data will be also the data belonging to the world data. So it will work very well, actually. This is kind of the ideal thing. So if the trained data is very large in scale, then overfitting to that large scale data is not that bad, because that model will be well generalized to the testing data, because testing data also will be similar to, or the testing data will be also one of the world scale, large scale training data. So if the training data is very large in scale, overfitting will not be that bad thing. So in that philosophy, this data augmentation is increasing the number of the training data, and eventually we are wanting to make this training data follows the world distribution. Okay. So in that philosophy, this data augmentation is somehow relieving the generalization problem. Okay. So the philosophy is, if the model can overfit to the world scale data, then it is actually good. But the thing is, if the data becomes larger, the model will not easily overfit to the large scale data. That's another problem, actually. So anyways, this data augmentation is helpful for relieving the overfitting phenomenon. So that's why here data augmentation schemes are proposed. Okay. So, and also dropout is also proposed in this AlexNet. And actually, in the middle of the FC layers, here we are having the convolutional layers in the CNN architecture. The first part is the convolutional layer. The later part is the FC layer. Given the data, I mean, making this architecture overly fit to the trained data happens when the data scale is limited. But given the limited data scale, if we can involve some layer that provides some randomness during the training, then this architecture, because of this randomness, will not get 100% accuracy for training data. Okay. So on purpose, by involving this layer, which have some randomness, we are trying to prevent having 100% accuracy for the train data. And actually this dropout is used only for the train, and not for testing. Okay, so dropout is proposed to prevent having 100% accuracy, 0% error rate for the training data. Okay, so it involves some randomness during the training. How to do that is, after the FC layer, you involve some dropout layer, okay? And this dropout layer, what they do is they, on purpose, turn off some signal propagation. So, for details of this dropout, you will learn it in the later slides, maybe next lectures. Okay, so I will explain that in detail after that. But the conceptual thing is, in dropout layer, you will turn off some of the layer. So actually, these functions are y is equal to x. So from previous layers output, it generates some output. Okay, but for some of the node, you will turn off their propagation randomly, and during training, this turn on, turn off, this is randomly decided. So because of this, during the training, you will not get the 100% accuracy or at 0% error rate during the training. So this dropout layer is on purpose preventing this 100% accuracy during the training. Okay, and this, anyways, we will explain that in the later slide, later lecture in more detail. But anyways, dropout is proposed, and also the data augmentations are proposed to prevent the overfitting. Okay, and ReLU is first used to prevent the gradient vanishing I explained, and also to accelerate the training, multi-GPUs are used. Okay, and thanks to that features, this AlexNet was the first architecture that records the state-of-the-art accuracy in ImageNet challenge. Okay, there was actually 10% gap between these. Okay, and actually this is the AlexNet architecture, the definition of the AlexNet architecture. And the thing, this here we define the structure of the architecture, and it is also composed of two main parts. This is the convolutional layers, which process 2D signals, and here is the FC layers that process one-dimensional signals. Okay, and in the middle you can see there's dropout layers. The detailed operation I will explain that in the next lecture. Okay, so previously there was no dropout, only linear and nonlinear activations are there, but here there's dropout to prevent 100% accuracy for the training step. For the dropout, they only randomly turn on, turn off the layer propagation, only training, and at the testing, they turn on all the signals always. Okay, so for the testing, it is not doing this kind of random things. Okay, and also you can see the ReLU layers are used as the activation layer for both convolutional layers and also the FC layers. Okay, and also max pooling instead of the average pooling is used here. And most of the operations are composed of Conv2D layers. So this is the definition of the AlexNet. Okay, and forward function, you do make first apply the convolutional layers, and after that, this average pooling is actually, I mean, from the convolutional layers, the output responses in the middle is small dimensional 2D channels with some channel number. Okay, so I mean, in the first layer, their inputs are image size, maybe 256 by 256 or 224 by 224 sometimes. And by applying convolution operation multiple times, we can reduce the dimension of the 2D signals and having multiple channels. So this would be the output X here. After applying convolutional layers, the response size would be like this. But if you apply average pooling on that, this will become 1 by 1 signal, okay? And you have the same number of channels, okay? Average pooling is doing that actually. So this is 6, so maybe this response would be 6 by 6. And so this will average this 2D two-dimensional response to this 1 by 1 signal by averaging the values here and only retain the number of channels. And then you will flatten the signal and apply the classification which is composed of the FC layers. That's the AlexNet architecture. Okay, so, and you can use this code to actually define and initialize the AlexNet, okay? So are you guys following this? Okay. And another important architecture is the VGG network. So this was AlexNet, okay? The one that recorded the best in 2012, that's the AlexNet. But next important architecture is VGG net, which is proposed in 2014 and actually have enough gap to AlexNet and have 19 layers. So this has the 8 layers. So actually, if you count the number of layers here, 1, 2, 3, 4, 5, 1, 2, 3, that's the 8 layers. So I mean, even though you have activation layers in the middle, we count only the convolutional layers. We somehow think these 3 layers are 1 step, 2 step, 3, 4, 5. So we are saying that the convolutional layers are composed of 5 layers. And we also think linear layer as the 1 layer. So here there's 1 to 3 layers. So this is why AlexNet is said to have 8 layers. So here we are saying that's having the 8 layers. But VGG network, it tried to investigate the relationship between depth of the network and overall accuracy. So it's the deep learning architecture. So if it goes deeper, the researchers think like that. If this architecture, deep architecture, becomes deeper, the overall accuracy may become better. So this is the assumption of the deep learning researcher, and this VGGNet actually investigated. So AlexNet, it have 8 layers. The VGG 16 architecture, it has 60 16 layers, and also there are a variant for this VGG architecture. So 16, VGG 19. These numbers are actually showing the layers, number of layers. And there's also VGG 11. So it has 11 layers. So anyways, compared to the AlexNet, they made a few variants by stacking more convolutional layers, okay? And then experiment with the relationship between depth of the network and overall accuracy. And mostly they use the convolutional layers with filter size 3 by 3, and also use pooling for max pooling, and also use the fully connected layer at the last part. Okay. So this yellow is denoting the convolutional layer, and green is denoting the FC layer, and this is actually input image. So from the input image, you will apply convolutional layers and apply FC to get some output, right? So here, the same. We increase the number of convolutional layers and apply the 3 layers of FC layer and get the final output here using the VGG network. But most of the convolutional layers, we will use 3 by 3 convolutions. So this is the VGG-NAND architecture and our definition. So, so we actually, this is the actually VGG 16, which have the 16 layers. And we will first define 5 blocks, okay? 5 blocks using the convolutional ReLU and max pooling layers. Okay, this is the first block, and second block is also composed of multiple convolutional layers and activation and max pooling. Block 3 is also same. Block 4 is also same. Block 5 is also same. And in the forward function, this is the FC layer definition. So linear ReLU, dropout, linear ReLU, dropout, linear. And forward function, you first sequentially apply block 1, 2, 3, 4, 5 we defined, which is the convolutional layers. And then here we flatten the signal and apply the FC layer. And after that, apply the softmax to make it into the probability vector, okay? So this is the VGG net. You can find that because this block 1, 2, 3, 4, 5 have the more convolutional layers compared to the AlexNet, it is getting bigger, actually deeper. And also you can see their corner size are mostly 3 by 3. Okay? The filter corner size is 3 by 3. All the filters are 3 by 3. And they are actually saying that this 3 by 3 filter corner is effective for stacking the layers. So they use this. Okay, so this is the VGG network, and indeed, its performance is getting better than AlexNet. Okay, by stacking more layers, its performance is getting better. And the next thing is the Google LUNET. Okay, so actually it is frequently called as Google LUNET. So somehow merging these two LE. So this is called as Google Net, but they are doing some naming strategy. I mean, to remind of this LUNET architecture, which is actually the oldest CNN architecture. So anyways, so they, LUNET, after LUNET, this LUNET was proposed in 1980s. But after that, the shallow running algorithm prevails and the deep architectures are forgotten for a while. But this time they somehow, proposed the new deep architectures and somehow remind of this LUNET architecture. For that, they said they do this naming strategy. Anyways, this is for understanding the Google LUNET, the important thing you have to understand is this inception module. This is called as the inception module, which is depicted in this figure. And this is the previous layer's response. And using previous layer's response, you have to apply 3 types of operations. The first is 1-by-1 convolution, 3-by-3 convolution, and 5-by-5 convolution, and 3-by-3 max predict. And then you will concatenate their response. This is the inception module, which is the basic module for the Google LUNET. And actually, in Google LUNET, AlexNet and Vision network, they stack convolutional layers, and also the Conv2D and also the F layers. Okay, that's kind of standard for this AlexNet, VisionNet, and LUNET architecture. But Google LUNET, they stack this inception layer multiple times, actually 22, and constitute 22 layers actually. And they are saying that they are having less parameters than AlexNet, but their accuracy is better. And also they don't use FC layers. Okay, so actually this this Google LUNET is also proposed in 2014, and that performance is also slightly better than VisionNet we just saw. Okay, so VisionNet is 7.3. VisionNet. VisionNet is proposed in Oxford, and the accuracy of Google LUNET is slightly better than that, and having 22 layers. And this is the implementation of the Google LUNET. So in the constructor, the thing you have to define is this inception module. Okay, so we first have to define the inception module class. Okay, so as I told you, it has 4 operations: 1-by-1 convolution, 3-by-3 convolution, and 5-by-5 convolution, and max predict. Okay, we have to define these 4 types of operation and apply it to input signal, right? Using this code. 1-by-1, 3-by-3, 5-by-5 convolutions, and max predict, we have to apply to the previous layer's response and then have to concat them. Okay, and that's the output of the inception layer. So this is the implementation of the inception module. And using this inception module, you will define the Google LUNET. Okay, so this is the first layer, second layer, third layer, fourth layer, and fifth layer of the Google LUNET. And this is the F layer. They said they don't use F layer, but indeed they have one linear layer at the last part. And at the first layer, they stack multiple convolution and max predict layers only. But from the second layer, they input the inception modules. Okay, they apply multiple inception modules in the later part. Okay, and then apply dropout and one linear layer. So if you see how they forward the signal, they first input the image into the first layer and apply it sequentially to second, third, fourth, and fifth layers that mainly constituted with the inception module, and flatten the signal and apply the FC layer, which is this. Okay, and then return the output. Okay, so are you guys following this? Okay. So this is the LUNET implementation, and they are insisting that thanks to this inception module, they are having less parameters than AlexNet, but outputting better result compared to them. Okay, so this is the Google LUNET, but I mean, both Vision network and Google LUNET, they are better than the AlexNet, but and they somehow experiment with more layers, deeper layers, how they affect the accuracy. Okay, but thing is, still there are some limitations in this bridge network LUNet. This is very important actually. So let's say this is the 8-layered architecture performance. If we stack more, this is the training error and testing error, and this is the number of epochs. Okay, so during training epochs, you can see their training error and testing errors are gradually reduced after the training epochs goes. But thing is, the 8-layered architecture, their training testing curve will be like this. As training goes, their individual errors are gradually reducing, but if we stack more layers, their curve looks like this as well. As the training goes, their training error and testing error becomes reduced, but I mean, their starting point will be better if we stack more layers. Are you agree with that? Okay, if we stack more layers, their performance that could be a lot reduced compared to the less deep architectures. But this kind of strange thing happens after we stack more than 20 layers. The performance of that architecture is becoming reduced again. Okay, so I mean when the layers are less than 20, their performance is becoming better if we stack more layers in the deep architecture. But if we stack more layers, more than 20 layers, then its performance is getting inferior compared to the 20-layer architecture. This is very strange phenomenon at that time. Okay, so we normally think if the architecture becomes deeper, the accuracy would be better. But if we stack more than 20 layers, if we make the architecture steps more than 20, then the accuracy is again reduced. Okay, so this is very strange phenomenon, and actually that is called as that is because of this vanishing gradient phenomenon. So this is actually very important, and this is the last topic for this lecture. So this vanishing gradient is very actually important that prohibit the proper training of the deep networks. So let's say here is the 20-layered architecture. This is the input image, and we have to calculate loss during the training. And for using that loss, we have to update this parameter sector for deep architecture. So we have to actually calculate this DLD sector, right? But when calculating this, somehow, because this deep architecture is composed of 20 individual layers, we will do this kind of thing. So let's say this is sector 1, the first layers parameter. So we can say sector is composed of sector 1 to sector 20. Okay, so the parameters for layer 1 to layer 20 parameters. Okay, when we calculate DLD sector 1, it requires like so let's say this is Y20 and this is Y19 and this is Y1. Okay, so let's say this index is saying the individual layers output. Okay, so I mean when calculating this, we have to somehow calculate so we have to, by the chain rule, we have to calculate this things. Are you agree with that? Okay. And normally, these gradient values are less than 1. I agree with that. Okay. So if you multiply some floating value 20 times, this term may have 20 or 21 or 22, right? So if you multiply the floating value, which is less than 1, 20 times in the computer, then their precision cannot properly represent their value because they may become very close to 0. Okay. Are you agree with that? Okay. So if you stack more than 20 layers, this calculation may become unstable. I mean, it eventually will go to 0. Okay, are you agree with that? Okay, are you understanding? Okay. I mean, when updating one parameter, you need proper direction to update that specific parameter. But if this direction goes to simply 0, then the training will not happen properly. Okay. If this is 0, then the parameter will remain same as the old one. Okay. So if you stack more than 20 layers, this gradient will eventually go to simply 0 because of the precision the computer can represent. So that's actually called as the vanishing gradient phenomenon. Vanishing gradient is vanished and it eventually goes to 0. Okay, because it multiplied some floating value less than 1 multiple times. So it eventually goes to 0. And we cannot properly update the parameters. Okay. So this happens actually, and this made this strange phenomenon. Okay. So deep architecture have to be better if we stack more layers, but because of this vanishing gradient effect, if we stack more layers than 20s, it tends to degrade the overall performance. Okay. So here the ResNet, which is proposed in 2015, that proposed very interesting method to prevent this kind of phenomenon. Okay. So this is the original deep architecture. Okay. So from the previous layers output, you apply convolution and ReLU convolution to output h of x from the input x, right? This is the plain layer we are using in AlexNet or BridgeNet and others. But here they propose some residual blocks. And here what they add is this kind of simple route that propagate this original signal x and add it to their original output. Okay. And by this simple addition, this gradient now becomes stable. I mean, I will explain that. So h of x, this is now the new output. Okay. fx is the, this function was fx. This function, applying this series of this operation, we record that as fx. So now the new output h of x is fx, applying fx plus the original signal x. Okay, I agree with that. Here, we will, if we calculate the derivative of h of x, then you can feel that you will see these things. Okay, so this could be less than 1, but x, because we add the original signal to the output, their derivative to the original input was 1. So this is new gradient. This could be less than 1. Can have very small scale. But because the original signal was added to the output, somehow the new gradient will be buried to 1, okay? Because this original signal is added to the final output, their derivative is 1. So the new gradient will be buried, by regarding this 1 as the mean value, okay? So now this gradient will be not very small in scale, but will have some value buried to, this 1 value. So if you multiply gradient values, which is varied from 1, so the overall gradient will also have the value slightly varied from 1. Okay, are you agree with that? So even though you multiply more than 20 terms, this gradient is not anymore vanished. Okay, so thanks to this feature, ResNet, they could stack 34 layers, and also ResNet have models that have 101 layers or 152 layers, and so on. Okay. So this is the plane. If we stack the 34 layers with the plane operation, it looks like this. But this is the 34 layered architecture with the residual connection. Okay. So this is actually the ResNet architecture. And this is a visualization for the VGG19. And now this statement is getting valid again. If we stack more than 20 layers, anyways, more layers, then with the residual connection, then the accuracy is now again become better, okay? Because we somehow prevent the vanishing gradient effect properly using this residual connection. So now, anyways, the deeper layers are getting better performance than shallow network. Okay, and this is the definition of the ResNet architecture. So I will explain this in the later lectures. Okay, so later lectures maybe after the midterm. So before that we will not. We use this ResNet code anyways. So next Monday, we will have quiz 1. Okay. Are you already getting emails for that, right? So